In this video, we are going to talk about some of the properties of convex set. So I'm going to talk about 4 properties here. The first one is arbitrary intersection of convex sets is convex. Then Cartesian product of arbitrary family of convex sets is convex. Interior enclosure of a convex set of convex sets is convex under the Euclidean topology. And lastly, sum of 2 convex sets is convex and scalar product of a convex set is convex. So I am going to show the proof of 2 of these theorems here. So let's get started with the first one. Arbitrary intersection of convex sets is convex. So let's say we have xi representing a family of set. So now this can be a family, it can be a finite, infinite, a power set, anything. Let's assume xi, where I is an element of the big I, represents a family of convex sets. Now we take so basically we consider the intersection of all these family of sets that we are considering in our current setting, and let's say we represent them by this sign, intersection of xi, where I belongs to big I. So now according to the first theorem, we have to show that this is convex, that the arbitrary intersection of convex sets is also convex. So let's pick any 2 elements x and y which belongs to this intersection. And let's pick a lambda that belongs to the closed set 0, 1, closed interval 0, 1, sorry. And we need to show that lambda x plus 1 minus lambda y also belongs to the intersection of all the xi's. And if we can show this, then we have shown that the intersection of convex sets is also convex. So now we have x and y, which are elements of xi for all I. Why? Because x and y are elements of the intersection, and since they're intersection, that means they belong to all the xi's. Alright, so since xi is convex for all I, remember we started with a family of convex sets, so all these individual xi's are basically convex sets. So we can write and if this is true, then we can write thus proved. So we have finished the proof here. I'll go over it and explain it with a diagram right now. So let's say we have this coordinate plane and we have these two sets which are both convex sets. So let's say we have this set x1 which is convex and this set x2 which is convex, and the theorem says that the arbitrary intersection of these two sets will also be convex. And we can see the intersection of these two sets is represented by this shaded area. So in this current setting, this shaded area represents intersection of xi, which is in this case is intersection of x1 and x2. Right, and now what we are doing is, let's say we are picking any 2 points which are here. So we are picking x here and y here. Let me clean this up a bit so it's visible. So let's say we are picking an x here and an y here, and the way we proved it is that we showed that since x and y belongs to this intersection, that means x and y are also belong to this individual sets x1 and x2. And since these individual sets x1 and x2 are convex, so we can take convex combinations of x and y and they will still be contained within these sets x1 and x2, which means the convex combination of x and y will also be contained within this shaded region, which represents the intersection of these two sets. Visually, if we take a look, then if we pick any points on this set, then and if we draw two lines, then all the points sitting on this line will be a part of this set. So that's how we prove the first theorem. Arbitrary intersection of a family of convex sets are also convex.